Hi everyone, welcome back. So in this video, I'm going to discuss about the Simplified Advanced Encryption Standard, and I will also try to demonstrate the operations that are involved in the encryption process with a simple example. If you ask me why are we bothered about studying this S-AES rather than studying the original Advanced Encryption Standard or the mostly known AES algorithm itself, my answer is simple. To better understand the operations that are involved in AES, which works on huge block sizes and key sizes, I thought of explaining this with a numerical example. More or less, both are having the same kind of operations, and the operations that are involved within the rounds are also almost similar. So if you work this and if you understand this, it makes our job much more easier analyzing the actual or the original advanced encryption standard algorithm. This was published by Musa, Schaefer, and Wedig in 2003. Their main purpose is also to enable students understand the AES better by using this as an example, and also they can do several numerical examples on the operations that are there. So S-AES can be used for better understanding of the original AES algorithm. If you can see here, this is the entire structure which involves both the encryption process and also the decryption process. Here, if you can see, I have mentioned there are two rounds. So the S-AES is a two-round algorithm which uses a 16-bit key to encrypt 16-bit blocks of plain text. In other words, here the block size is 16 bits. The block size is 16 bits, and also the key size that we are going to use is 16 bits as well. Okay, so the encryption algorithm involves the use of 4 different functions or transformations. You can see the first one is something called as add key, which is here, add round key, and nibble substitution ns, shift row, and mix column operations. We will see each one of these operations individually, and we will do a numerical example also to have a better understanding on how these things work. And also another thing is the initial 16-bit key that we are selecting will be expanded so that I will get two other keys of again 16 bits in size to be able to use during these add round operations. If you can see in the encryption procedure, there is one add round key function here. There is the second add round key function here. And there is also another third one, which is another add round key function. So in total, I will be requiring 3 keys. So 3 keys, each one of 16 bits each. So I require a total of 48 bits. We'll see the key expansion also, how it is going to work. So this is the just general overview of the structure. 2 rounds, which starts with an add round key, and round 1 has got 4 operations. Round 2 has got 3 operations. The decryption process is almost similar to the encryption process, but the round keys are employed in the reverse order. And there are some certain differences, which I will discuss in the last slide. Okay, so let us start. Each function operates on a 16-bit state treated as a 2x2 matrix of nibbles, where 1 nibble equals 4 bits. The initial value of the state matrix is the 16-bit plain text. As I told you, the block size is 16 bits, isn't it? So here we are talking about the plain text is 16 bits, and these 16 bits, if we assume that writing them as B0, B1, so on till B15, isn't it? The 16 bits, if you can imagine them as B0, B1, B2, so on until B15, if you write them in this particular format, B0 to B3, these are 4 bits, these are another 4 bits, these are another 4 bits, and these are another 4 bits. The total of 16 bits are treated as a 2x2 matrix. This is a 2x2 matrix of nibbles. This is one nibble, this is another nibble, this is another nibble, this is another nibble. So the entire 16-bit plain text is now organized into a matrix or 2x2 matrix of 4 nibbles. Okay, we will be performing our operations on this. This is called as a state matrix. This keeps changing after each and every operation, and the final state matrix will be our ciphertext. Okay. Now, see if you want to encrypt the plain text. Okay. Let us say that I want to send a message OK, which is my plain text. So OK, so O's ASCII value. If you take O's ASCII value is 110 and K's small k I'm saying ASCII value is 107. If you put them into binary, you get this, isn't it? And this is the case binary value. Now, these are 16 bits, isn't it? So these 16 bits are now arranged in the form of a state matrix. So 0, 1, 1, 0, and the next four ones. So the first four bits are written here, B0, B1, B2, B3, and the next four bits, B4, B5, B6, B7 are written down here. And next, B8, B9, B10, B11, B12, B13, B14, B15. So this is now my state matrix, and this will be passing through my operations. Okay. This is how a plain text is converted into the state matrix. Now, the 16-bit key is similarly organized, but it is somewhat more convenient to view the key as 2 bytes rather than 4 nibbles. The expanded key of 48 bits is treated as 3 round keys whose bits are labeled as follows. As I told you, there are 3 add round key operations. In our structure, we found that there are 3 add round key operations, isn't it? So for these 3 round key operations, we need 3 keys. Each key should be of length 16 bits. So I need a total of 48-bit keys. In order to get 48-bit keys, I have to use my initial key, which is of 16 bits. The first 16 bits are the original key which I have selected will be used as my first round key or round 0 key. And from these we will have another key expansion algorithm where I can generate 2 distinct round keys called as round 1 key, which is K1, and the round 2 key, which is K2. So in total, we'll get, you can see. So these are my 2 words, W0 and W1. Each one is 8 bits long. Okay. So the first, my initial 16 bits will be my first round key. And from these, I will start expanding these 16 bits into my remaining 2 round keys, where the next 2 words will be my K1 and the next 2 words will be my K2. Each one of these is 16 bits in length. So each word will be 8 bits. Do not get confused. Once we start working on the problems, it will be much more easier. So why we are organizing all these things is to make these operations easier to analyze and also to calculate. Okay. As of now, I just told you that 16 bits plain text arranged into a 2 by 2 matrix of 4 nibbles. Similarly, 16-bit key arranged into words. And from these words, we can see that it can get expanded up to 3 round keys. Okay. Now, let me go forward. So this is the key expansion algorithm. How do we expand a key? So let us take an example and first see how it happens. And then we'll go into the encryption process. These 2 diagrams I collected from the internet. I thought of this gives you a better understanding on how the key expansion works and what are the processes that are involved in getting the remaining round keys. Let me show you the formulas. As I told you, the first 16 bits, which is initially selected by the user, are this is the first 8 bits and these are the second 8 bits, W0 and W1. We have them both. So automatically my K0 will be W0 and W1, my 16 bits, isn't it? So to complete this, what I need is I need K1, which will be W2 and W3. And then I will also need for my third one, W4 and W5. So how do I calculate these operations? How do I calculate these words which are 8 bits long? These are the formulas. So W2 can be calculated as W0 exclusive OR with G is the function. G function on W1. So what is this G function? You can see in the diagram here. Here, if you see, G function accepts a word which is of 8 bits. So this is of 8 bits. This is the G operation. What happens to these 8 bits? So if you give W1 as an input, what it will do is it will first divide it into 2 halves, 4 bits and 4 bits. And these 2 are interchanged or simply circular shifted. So we move both the halves onto one other side. That's all. And then both these 4 bits are now subjected to S box operations. And the output also will be 8 bits here. 4 bits and 4 bits. And the total will be 8 bits. So these 8 bits are now performed an exclusive OR with something called as a round constant. We call this as a round constant, shown here as RCon. We are showing this as the RCon. And finally, you get the next word. So let me show you. Now, W2 is obtained as W0 exclusive OR with this G operation on W1. So what is this G operation? You take W1 as an input. You first rotate the nibble. You first rotate the nibbles of W1 and then perform the substitute nibble. Whatever value you get here, you perform an exclusive OR with the round constant 1 and then an exclusive OR with the W0. Similarly, W3 is obtained as exclusive OR operation between W2, the one just we calculated. You can see the one just we calculated here, and the W1 value. You get W3. So here, once you obtain W2 and W3, automatically you will get the for round 1 key, which is K1. Similarly, W4 is also calculated using W2 plus GW3 and W2 plus round constant 2 plus substitute nibble, rotate nibble of W3. The G function remains the same except for the input. Earlier we took W1 as input and this one we are taking as W3. And then we calculate W5, which is W3 exclusive OR with W3. You can see here. Once you calculate W4, you take this as an input to the exclusive OR function with W3 and then you get W5. Once we have W4 and W5, you get the next round key, which is K2. So what is this round constant? Let me just remove this here. Okay, you can see this here. So RCon is a round constant defined as follows. How did I get this RCon value? From where did I get it? So RCon is defined as, or the round constant I is defined as x power I plus 2 mod x power 4 plus x plus 1. Now for the first one, what do? I simply put 1. Isn't it? Round constant 1, I is equal to 1, which makes this 1 plus 2 x cube mod so. So because x cube has a degree less than your mod, less than your polynomial degree, this is accepted. And x cube can be written as 1, 0, 0, 0. How did I write this? See, x cube's constant is 1. There is no x square component, so 0. There is no x component, so 0. There is no 1's component, so there is 0. So I have 1, 0, 0. Similarly, if I want the round constant 2, RC2, then I would place here x power 2 plus 2, which gives me x power 4. As x power 4 is equal degree of your mod value, this has to be reduced. So what do I do for reducing? I'll simply subtract. Just divide this by this. So what would I get? If I divide this, I get x plus 1 that is remaining. X plus 1, how can I write in binary? There is no x cube. There is no x cube component, so 0. There is no x square component, so 0. X component is 1, so 1. 1's component is 1, so 1. These are, you can see, RC of I forms the leftmost nibble of a byte. We need a byte here because we are exclusive OR with 8 bits. We need 8 bits for round constants also. So this, I got the first 4 bits. The remaining 4 bits are 4 zeros. You can see with the rightmost nibble being all zeros. So I'm having 4 zeros on the right hand side. So I'm just adding 4 zeros, which will give me my round constant 1. And so this is my round constant 1, which I can use. And this is my round constant 2. This is how we obtained these two values. Okay. And we can employ them. So let me show you a numerical example on how to calculate this. So let's start with, let us suppose that the key is 2D55. This is written in hexadecimal. So let me write it in binary. 2 is 0010. D is 1101. 5 is 0101. And again we have 5. So 0101. This is my key. This is my 16-bit key which I selected. So automatically these 8 bits, the first 8 bits come under W0 and the remaining 8 bits come under W1. So this is my round 0 key. The first key which I am going to use is this. So I have my values of W0 and W1. Now I have to calculate what is W2. If you imagine, if you remember, what is W2's value? W2 is obtained from W0 exclusive OR with G of W1. What is G of W1? I told you W1 rotatable, substitutable, and then round constant 1. So if you employ the values, so W0, this is W0's value, this is ROR constant 1 value, and this is W1 value. What does rotatable tell you? You have to shift this to here, and this comes here. But in our example, as we are having both identical values, you don't find any change here. With this rotate nibble function does not show you any kind of difference. So moving on to the next step, this is done. So now it is saying that substitute nibble of 0101 and 0101. So what you have to do is there is an Xbox in S-AES. So if I give as 0101 function or 0101 as an input, what you can see here is the first 2 bits will tell you to look for the row and the remaining 2 bits will look at the column. So 01 is here and 01 is here. So you have to replace it with the value 1. How do you replace it with the value 0, 0, 0, 1? Similarly, this is also subjected to the substitute nibble operation. Once again, because these two are identical, you get the same value of 1. So 0, 0, 0, 1. So now you have your W0, you have the round constant 1, and you performed the G operation on W1 also. You got everything now. Okay. So you do an exclusive OR, you get W2 value. Do check it out. So 1, 0, 1. See, 0. And then you can see 0, 0, 0. You can do this parallelly, or if you want, you can write it down like this and also do the same operations. This is how you get W2. So W2 is only 1/2 of your second round key or the first round 1 key. For the second half, you have to find out what is W3. W3 is pretty simple. Whatever you calculated W2, exclusive OR with the original W1. Straightforward, you get this answer. So now your round 1 key, which is K1, is 1 0 1 1 1 1 0 0 and 1 1 1 0 1 0 0 1. That is how you calculate. Similarly, if you proceed on the same things, W4 is equal to W2 plus G function of W3. Once again, you have the round constant and rotate nibble. You can see here, W3 we calculated. I just substituted the value for W3 and I just substituted the value of round constant 2, which we calculated in the previous slide. So what is going to happen here? Now these 4 bits are going to move here and these 4 bits are going to move here. That's all. That's what rotate nibble is all about. You can see 1001 110. Now this is substituted for substitute nibble. So what happens? 1001 has to go here. So 1001 2. So what is 2? 0 0 1 0. And this is 1110. What is 1110? 1110. We have F. So 1 1 1 1. See, check it out. This is what. And you perform an exclusive OR operation, you get the W4 value now. Once you have the W4 value, you have to calculate the next W5 value. It is straightforward. W5 is nothing but whatever value you calculated for W4, exclusive OR with the earlier value of W3. This is what. Now from this, what you can obtain? Your round 2 key, which is 1 0 1 0 0 0 1 1 0 1 0 0 1 0 1 0. Similarly, the first key that I am going to use is my original value, which I have selected 0 0 1 0 1 1 0 1 0 1 0 1 0 1 0 1. So from a 16-bit key that I have, now I have expanded or I have generated 2 distinct round keys, each of length 16 bits. So now I'm having a total of 48 bits, which I am going to use as my 3 round keys as an input to my add round key operations. So this is regarding the key expansion part. Now let us go into the encryption part of the AES, or the simplified AES algorithm. Now let me start bit by bit. If you can see, we have to select a 16-bit plain text, and then we start giving this as an input to this particular operations in this particular order only. Now for this calculation, I have selected another key, which is 0100 1010 4 ones 0101. From this, if I do the calculation that I did in my earlier slide, you will get the same thing as K1 and K2. I'm leaving this for you as an exercise. Just try to find out if I did any mistake. I'm sure I didn't. And if you find any other mistakes, do ping me in the comment section. Okay. So let me start. The first operation is add round key. What do you do here? The add key function consists of the bitwise exclusive OR of the 16-bit state matrix and the 16-bit round key. The inverse of the add key function is identical because exclusive OR operation is its own inverse. We all know that. So what do you do, sir? Let me pick up a 16-bit plain text. My 16-bit plain text is this. What did I tell you? The plain text, the 16-bit plain text has to be organized into a form of an nibble and a state matrix. So let me write this down into this. See, this is it. These are my first 4 bits. These are my next 4 bits. These are my next 4 bits, and these are my next 4 bits. I have written this is my plain text, or this is my, let us say that this is my plain text, which is my original 16 bits. Okay. Now here I am getting W0, 1, which is my K0. So my K0 I am already having this here 01001 here. So I just written it down in the same value. The first 4 bits of the key here, the second 4 bits here, the third 4 bits here, and the fourth 4 bits here. Just perform a simple exclusive OR operation on this. So if you do an exclusive OR operation on this, it's straightforward. So 1 0 1 0 0 0 1 and a 1 0 1 and a 0 1. So this is my new state matrix after the first operation completed. After this operation is completed, now I got this. This state matrix is passed on to the next operation, which is your nibble substitution. This is straightforward. You just take the round key. You just have your 16 bits of plain text. You just have the 16 bits of key. Perform an exclusive OR. That's all. Nothing else. Now let me take you to the nibble substitution part. So what is a nibble substitution? As we just did during your key expansion algorithm, a nibble substitution has an X box to it. S box has got all the values, and you compare the values and you substitute those values into your state matrix. So an S box is a 4x4 matrix of nibble values that contains a permutation of all possible 4-bit values. So what are all the 4-bit values? You know, 0 0, so 0 0 0 till 1 1 1 1. So all these possible combinations are here. Each individual nibble of the state matrix is mapped into a new nibble in the following way. How do you map it? The leftmost 2 bits of the nibble are used as a row value, and the rightmost 2 bits are used as a column value. This is what we just did during your key expansion. The same operation we are going to do here. This is the X box. We just saw this, and let us implement this nibble substitution on our state matrix, which is 1001. Let's take this. So 1001. I told you that the first 2 bits, your leftmost 2 bits form your row, and the rightmost 2 bits form your column. So 1001, which is 2. So this nibble is replaced with 2. So what is 2 value? 0 0 1 0. Similarly, 1 1 0 1 is there. So 1 1 is here, 0 1 is here, and it can be replaced with E. So E is 14. This is the value of 14, isn't it? So 1 1 1 0. Because these two are also identical, you have the same 1110 1110. This is what we do in nibble substitution. It's a straightforward thing. But remember, during decryption process, we have an inverse S box. So inverse S box is used for the decryption purposes. I'll show you the example for decryption also. So this S box is used for encryption part, and this S box is used for decryption part. Okay. So remember that nibble substitution is nothing but if you take a 4-bit number, the first 2 bits will represent the row and the remaining 2 bits will represent the column, and at the intersection, whatever value is there, it is an hexadecimal value. You just write it down in the form of 4 bits. That's all. Straightforward. Now let us move on. So we completed these 2 operations here. This is done. This is done, isn't it? Now let me move on to the next one. So these two are done. And the third operation that we are going to discuss is something called as a shift row operation. The shift row function performs a one nibble circular shift of the second row of the state matrix. The first row is not altered. You have to remember this. During the decryption process, the inverse shift row function is used, which is identical. You simply move it back. That's all. Because it shifts the second row back to its original position. That means I'm just performing an inverse of the operation what I did here. Automatically, it comes back to the original position. Let me show you. So this is my state matrix usually. What I'm doing is, I'm going to leave this first row unaltered. I'm not going to change anything. This is the first row and this is my second row. I'm only going to take the second row and I'm going to perform a one nibble circular shift. So S10 goes here and S11 comes here. You can see this. These two are interchanged. Okay, these two are interchanged and that is what we call as shift row operation. So let us check it out in our state matrix. This is my state matrix. And if I do this operation, the thing is, because these two are identical, you might not notice any change in this operation. But we have to do this. This is a shift row operation. Understood? So this is also done. Next most important one is your mix columns. What is mix column? The mix column function operates on each column individually. Each nibble of a column is mapped into a new value that is a function of both nibbles in that column. The transformation can be defined by the following matrix: multiplication on the state matrix, where arithmetic is performed in Galois field of 16, where 1 means it's a polynomial 1 and 4 means it is a polynomial x square. And this is the polynomial that we are going to use to reduce your values. So let me show you what it is. It's simply that you take this matrix 1, 4, 4, 1 and you perform a matrix multiplication on the state matrix with this. But it is not straightforward in numerical multiplication. You perform this multiplication in Galois field of 16 or 2 power 4. And here, if I say 4, it means it is x square. Understood? And any values has to be reduced according to the mod x power 4 plus x plus 1. So you have to perform this operation. I'll show you how it is done. Okay. So this is what. This is your state matrix. What you get. Okay. And this is my mix column matrix. You perform an multiplication. And this is your new state matrix that you get after completion of the calculation. Let us start doing this. So imagine, please remember that this is our state matrix as of now. 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. Let me do it. See, this is my state. And now I have to perform this operation. Now you know that. First, let me take this value. How do you do this? So this into this, isn't it? So S00 can be defined by what? Or can be calculated by what? So 0, 0, 0 into 1 is 0, 0, 1, 0. Exclusive odd with 1, 1, 1, 0 into 4. As I told you, it's not a simple numerical calculation. All these calculations are in Galois field. So to find out what is the value of this 4 into 1110, I have to perform an polynomial arithmetic. How do I do that? As I told you, 4 into 110 can be written as, what is 4 in Galois field of 16? It is x square. Similarly, 1110 can be written as x. This is the x cube coefficient. So is there x cube? There is another one here. So x square. There is another one here. X. There is a 0 here. So x power 0 coefficient is 0. So I don't write it down. There is no plus 1. So 4 into 1110 can be written as x square into x cube plus x square plus x. If I do the multiplication, I will be getting this value, x power 5 plus x power 4 plus x cube. But what did I tell you? I'm going to use this particular modulo, x power 4 plus x plus 1 polynomial to reduce the values, because I'm talking about Galois field of 16. So to reduce this, what I need to do? I need to perform polynomial. You see, x power 5 plus x power 4 plus x cube. Whatever I got this value, I put it here. And I have to reduce this in accordance with this. So if I want to cancel out, I have to multiply with this with x. So into x, what gives me? X power 5 plus x square plus x, isn't it? So if there are two common elements, they cancel each other out. So there is no x power 5 anymore. And if what do you have? X power 4 plus x cube plus x square plus x. Now it is still the same degree. I still have to reduce it. I can only accept x cube or lower. That's all. So what is it? Because both the first degrees are equal, I can just multiply this with 1. So x power 4 plus x plus 1. So what do I get out of here? Once again, these are two same values. They cancel each other out. And there is another two common values of x. They cancel each other out. What I get is x cube plus x square plus 1. Now, because x cube's degree is less than x power 4, I can accept this. So I got this last value of x cube plus x square plus 1, which I can convert to binary as, tell me, x cube's coefficient is 1, so 1. X square's coefficient is 1, 1. There is no x coefficient here, so 0. There is a 1's coefficient, so 1. So x cube plus x square plus 1 can be written as 1, 1, 0, 1. Now, I only calculate this part, isn't it? So S0, 0 is given by 0, 0, 1, 0, exclusive OR with 1, 1, 0, 1, which gives me 4 ones. Similarly, if I want to calculate the next one, what is this? S0, 1. I have to do this calculation with this. So find it out. If I want to calculate this, it is 1110 exclusive OR with 4 into 11110. So this is the calculation I'm doing with this now. Okay. Now, because I just calculated this, isn't it? 4 into 1110. 4 into 1110, I just calculated this. So what do I get out of here? This is the same value. I'll get 11101. So 1101 exclusive OR with 1110. And this is my next value 0011. Okay. So next, let me calculate S10. S10 is this one. So 4 into this one, 0010 into 4. I'm calculating this column. So 0010 into 4 exclusive OR with 1110. Once again, you have to calculate this. So 4 is x square. And what is 0010? There is no x cube coefficient. There is no x square coefficient. There is only x coefficient here. So x square into x gives me x cube. Because the x cube's degree is less than our polynomial, I need not reduce it further. So x cube can be simply written as 1000, which gives me 1000 exclusive OR with this 1110, which is 0110. Similarly, the next calculation is also the same because I already did this here. I'm just replacing it here. 1101 exclusive OR with 1110, which gives me 0011. This is your mixed column operation. You have to do this like this 1441, and you have to remember this polynomial x power 4 plus x plus 1. All these calculations are done in Galois field of 16. So finally, after doing all this is my resultant matrix. Okay. I think I slightly got these things wrong here. So don't worry about it. This is actually 10. It's slightly wrong. So don't worry about this. But this is the actual order. So 4 1s here. And the next one is 0011. And here is 0110. And the last one is 0011. This is my new state matrix after completion of the mixed columns operation. Okay. So let me show you the next one. So this is done. I did the nibble substitution. I did the shift row column. I did the mixed calls column. And then I come up to the last operation in round 1, which is your round key. If you remember, I already used the K0 value here. And we already calculated K1 and K2 values. So this is nothing but this is my K1. The values that I calculated earlier, K1, I simply perform an exclusive OR here. So my state matrix exclusive OR with K1 results in this matrix. The new state matrix is this. You can see it's straightforward and exclusive OR operation. Nothing else is there. Round 1 is completed and then followed by round 2. So in round 2, the state matrix keeps following. So we keep on changing the state matrix. So this is also been updated. Now this matrix is passed on to the next round, which is your nibble substitution again. So let me show nibble substitution. This is my new state matrix. So 0010. This is 00 and this is 10, which is A here. and then 0, 0, A means what? 1, 0, 1, 0. 0, 0, 0, 1. So 0, 0, 0, 1, 4. You can see this is what? So this is A, this is 4. You can write it down in binary. Similarly, the nibble substitution is also done. Now this state matrix proceeds on further. What is next? It is shift row. Once again, we have two identical values. So you won't find much change, but technically speaking, these rows are circular shifted like this. But these two are identical, you don't find that change anymore. So this is also done. These two operations are completed. The last operation in round 2 is your add round key operation, where we are going to use K2. You can see K2, the one which we calculated is K2 is this. Once again, a 16-bit round key. And this round key is now exclusive OR with your state matrix. This is the state matrix. This is my state matrix. Okay. And this is performed an exclusive OR with my K2, which gives me the resultant. This is my ciphertext when I write it down in this format. First 4 bits 0010, the next 4 bits 0100, the next 4 bits 1110, and the last 4 bits 1100. So for the given plain text, after performing all these operations, so add round key, nibble substitution, shift row, mix columns, add round key, nibble substitution, shift row, add round key, I finally got my ciphertext, 16-bit ciphertext as this. So this is my 16-bit ciphertext, which I got after all these operations, which are divided into 2 rounds. So let me show you the decryption part also. The decryption part, you can see that add round key remains the same. This is an inverse shift row. There is an inverse nibble substitution, and there is an inverse mix columns. The main difference here is it can be the more or less the same time of operation, but the round keys are actually applied in the reverse order. The ciphertext, when you give it as an input, it will first accept K2 and then K1, and finally we'll have the K0. And also there is something called as inverse mix columns. In the mix columns, we multiplied with 1441, isn't it? Here, what we are going to do is we are going to multiply with, in the inverse mix columns, this particular matrix 9229. This matrix is the inverse of 1441 with respect to modulo x power 4 plus x plus 1. So we have to do with this. So the decryption process can be summarized as, first you perform an add round key with K2, then your inverse shift row, then your inverse nibble substitution. What do you mean by inverse nibble substitution? I have shown you an S box, isn't it? We have another decryption S box that is called as inverse S box. From there we have to do the inverse nibble substitution. And this is then you have the add round key with K1, and then you have the inverse mix columns, and then we have the inverse shift row, and then we have the inverse nibble substitution, and then the add round key with K0. So this is the summarization of the decryption algorithm. For our example, I did do the reverse order also, and if you are interested, please go through the same steps again and try to. I'm also giving, this is the inverse S box. This is the inverse X box, which you have to use for the inverse nibble substitution here and here. And this is the matrix multiplication, which you have to do for inverse mix columns here. And the same round keys can be used, which we calculated during our encryption process for decryption also. If you are interested, please do try out this and find out if you are going to get the same plain text or not. I did get it. So this is the exact plain text which we started our journey with. And I am able to get the same plain text after doing the decryption process also. So hopefully you will also get the same. And if you have any queries regarding this, please ping me in the comment section. Understanding this makes life much more easier when you're studying the original AES algorithm. In the next video, I'll talk more about AES and some brief history of AES and how it can be used. Till then, take care and good luck. Thank you very much for watching.